In this example, the sun subtends an angle of 0 degrees 31 minutes at the Earth, which is around 150 million kilometres away. What is this sun's approximate diameter? Now, picture somebody on the Earth is looking at both sides of the sun, where they can see both sides, and they're opening up an angle and seeing how big the angle is. It's a small angle, it's less than 1 degree, it's roughly half a degree. So we can use an approximation. You'll also notice that this around is used here, another clue that we can approximate. And as soon as you draw a picture, you'll realise just how inexact this problem looks. It's got a few things that aren't quite sitting right with me. If we've got 150,000 kilometres between the sun and the Earth, then I'm wondering, well, is that measured from where this person's standing to the edges here, the furthest point they can see? Because that'll be further away from the closest point. Okay, there's no need to think like that. It's a long way away, obviously a lot further away than the sun is wide. So this word around just helps us get around those little problems so that we don't get bogged down by them. We're making an approximation, okay? So labeling it like this is good enough. Now the first thing we need to do is change this into radians. So think through the fact that if you have 0 degrees and 31 minutes, you need to ask yourself, how many degrees do I have? Remember that the minutes are 60ths. So what we actually have here is 31/60ths of a degree. In other words, roughly half a degree. Does that make sense? Now I can take the number of degrees that I've got and I can multiply it by pi over 180. So that gives me 31 pi on the top and I've got 10,800 on the bottom. That's my angle in radians. So now I'm ready to work with it. Now we're going to do this 2 different ways just so we can see that there's variety and we can compare the results that we get with each way. The first thing I'm going to do is consider that if I draw a straight line here for the diameter, this is actually not a right angled triangle, is it? So how about we cut it in half, make it so it is a right angled triangle. I'll just draw it a bit bigger so it's easier to see. And instead of a diameter, we'd be dealing with a radius, wouldn't we? We've still got 150 million kilometres here. And now we've halved that angle. It'll be 31 pi, not over this number, but over a number that's twice as big, because if we double the denominator, we've halved the fraction. So this angle that's in here is actually 31 pi over, what have we got, 21,600. That's the size of the angle. Now we can use our right angled trig on this, because this is a right angled triangle. So we can say that the tan of 31 pi over 21,600 is equal to r over 150 million. All right, how do we get r by itself? We multiply both sides by 150 million. Now, as we go to do that, you can see that we're going to use the approximation that the tan of this number is actually very close to the number itself, because clearly we have a very small angle. So that means that our radius is going to be 150,000 times 31 pi over 21,600. And if that's our radius, then our diameter will be double that. So in fact, I could easily jump straight to that. Instead of having 150 here or 15, I can just change that to 30, a little bit cheeky. Now I've got something to put in my calculator. Before I do, it makes sense to cut the numbers down a little bit just so there's less to do. And plugging that into my calculator, I get 1,352,630. Remember, this is in kilometres. So the 0.17 is really not that relevant. We're talking about an extra 170 metres here. So rounding off to the nearest kilometre, let's just round both of those off. We have approximately 1.3 or so million kilometres. So the sun's pretty big. Now, if I actually compare this to the exact value that I would have got if I'd done the same calculation, but instead of making the approximation here, if I'd actually just put in the tan of that angle, well, the answer that I get is only 9 kilometres different. And out of 1.3 or so million kilometres, I don't think 9 kilometres is too much of a problem. In fact, that's much less of a problem than our whole issue of whether we were measuring this 150 million kilometres from here or from here. Because if the sun is more than 1 million kilometres wide, we've just gone and made it 500,000 different. We might be out by 500,000. So being out by 500,000 with this, or being out by 9 kilometres with this, you can see here that we're making an approximation. There's no point getting too bogged down. Now, let's do it a different way. We also know a formula for finding the size of this arc. If we saw it as an arc here and that this is part of a big circle, we could use the formula L equals R theta, where theta has to be in radians. So then the length of the arc, that's what we'd be looking at, that would be a good approximation for the diameter, would be the radius multiplied by theta, where we'd want the entire theta itself, 31 pi over 10, 800. And what you can see there is that it's the exact same calculation that we've just made. Obviously here our denominator was twice as big, but also we were multiplying by something that was twice as big. So this is going to give us the exact same answer, which begs the question, how do you decide how to do a question like this? Well, when we've got really large distances involved and really small angles, the answer is that all of your methods will tend to roll together and give you a very similar answer. And that really answers how and when and why we use these approximations.